Right. Just watch this closely. Okay. Right. Welcome. 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 Today. I've got 2 weeks, but I'm hoping not to spend the whole 2 weeks on this. Seems an overkill. But yeah. So today, tomorrow, and next week we'll be looking at chapter 10 in the book, and it's all about normal subgroups and things like that. It's another. 10.1 is normal subgroups and factor groups. What on earth is that good for? You'll see. We kind of decompose groups into simpler groups and then into even simpler. But that's only coming later. Okay, what we had was cosets. Do you remember what a coset is?
Partition.
Yeah, so each of the parts in the partition is called a coset, and they're all you always take an element of the group. Of a subgroup. Of course, you need a subgroup in a group G, and you take all elements that you fix a G, and you multiply everything in the subgroup by G, and you get a coset. So these are called left cosets, and all HGs for the different value of the little g are called right cosets. As a reminder. Now, on page 104, you had an example which says that it's not always true that left cosets and right cosets are the same thing. Okay? So when you took, it was the group S3 of all permutations on 3 elements, and you took A was the subgroup which only had these 2 elements, and the left cosets are these and the right cosets are these, and they're not the same. Fair enough. So now we're interested in knowing for which subgroups the left cosets and the right cosets are the same sets. So for K, it's not S3, but the question is for which subgroups the left cosets and the right cosets are the same. And it seems like an arbitrary question. Why should we be interested in this? But what happens is that these subgroups that are going to be called normal subgroups play some special role in the theory of groups. So let's have a look at them. And start by theorem 10.3. You can see that I've not done 10.1, but we'll get there later. Just want to do it in a slightly different order than it's in the book. So let G be a group, and H a subgroup of G. Then the following are equivalent. Do you know this abbreviation? Acronym. The following are equivalent. . Number one, no matter what element of G I pick, the left coset is the same as the right coset. Subgroup H, defined by this element of G. 2. No matter what element of G I pick, if I look at G, H, G inverse, so that's everything in the group that has the form G little h, G inverse for some h in H. And that's the set. So this is the definition, G, H, G inverse. H go through all these. So that's not yet the statement, but this is a subset of subgroup H. So all such elements, you pick anything in H and anything in G, and you do this product, G, H, G inverse, it's in the subgroup H. And the third statement that's equivalent is that no matter what element of G I pick, this G, H, G inverse is actually equal to H, rather than just being a subset. Okay, so if it's a subset, it has to be. That's the theorem. Proof. Any questions so far? If you have questions anytime, just shout them. Okay. What does one do to prove a statement which is this and this and this are equivalent conditions?
Assume one proves
Assume one prove the other?
Assume one, use that for the next one. It literally.
Yeah. Is that the same thing?
I just prove both ways.
Yeah, both ways. If you have 2, or if you have 3, then you do like a, well, you can do whatever you want, but you have to make sure that you get what in graph theory you'd call a strongly connected digraph. So you can get from any to any by a chain of implications. So in this case, what we're going to prove is 1 implies 2, implies 3, implies 1. So we're proving 3 implications, and then we have the equivalent. Okay, so to prove 1 implies 2. Let's have a look. So what do we need to prove? We're assuming that any left coset is the same as any right coset. We're trying to prove that any element of this form, GHG inverse, is in H. Okay, so let G be any element of G, and H be any element of H. And so what we need is that GHG inverse is in H. That's what 2 states. What do we know? We know that G times H is equal to H times G. So we can find some H dashed in H such that GH equals H dash G. Okay. This is in this coset. This coset is equal to that. So there has to be a witness for this element being in that set, and that witness is H dashed. So we've got this witness, and what do we do with it? We look at the GHG inverse. Now GH is H dash to G. And this is all still multiplied by G inverse. Now, G times G inverse is the identity, so this is H dashed, and this is in H. And that's it. So it actually turns out that the product, GH, G inverse, is equal to that witness that we have here. That's the proof. Okay. Next, 2 implies 3. So again, we have G. So we're trying to prove that 3 is true for any G, so we fix one, but arbitrary. And we know by 2 that this is contained in the subgroup H. So what remains to prove, we still need to prove that H is a subset of GHG inverse, and then one is the subset of, well, they're both subsets of each other, and they have to be equal. Okay, so to prove this, we take any element of H and we prove that it's also in this set, and that shows up as a subset. Okay. Now again, by 2, but now we do the 2 for G inverse in G. Okay. We're using the fact that for every G, this is true, we're applying it for not this G, but its inverse. So what we know is that G inverse H. G is a subset of H. So in particular, with this H, if we do this, this has to be an element of the subgroup H. And now, and from this it follows that, what is H? Well, this is a bit of a tricky thing. So H is equal to G times this thing times G inverse. Because by associativity, you can do this and you get the identity, again you get the identity, so it's H. And now the bracket is in the subgroup capital H. So this whole product is in G, H, G inverse. Well, as we wanted to prove. Okay. So there's nothing really illuminating there. It's just manipulating symbols. Any questions? What just happened? Okay. So we want to show that 2 implies 3. Okay. So to show 3 holds, assuming 2, we fix an arbitrary element of G. because we need to show that this is true for any G. So let G be any. We know that this set is a subset of H by the assumption. So we only need to show that H is a subset of GHG. So to show that H is a subset of G inverse, we take any element here and prove that it's also there. That shows that it's a subset. That's the definition of a subset. So take anything in H. And we're trying to prove that it's in this set. Now, what we do is we write H in this way. G inverse, H, G inverse. G inverse is the identity, G inverse is the identity, so it actually is H. Now, if we can show that this bracketed thing is in the subgroup H, then G inverse is in G, HG. Okay, and that's the goal. That's what we're trying to do. We're trying to show that H is in that set. But the only thing we need is that this actually is in H. And to show that this is in H, we use that again. But this time we're not applying it to G, but because it holds for any G, it also holds for G equal, well, not G, but not G equal G inverse, but it holds if you put G inverse there and G there. So this is in, okay? That's the thing. And the last implication that we want to prove, 3 implies 1, and goes like this. So what do we want? We want that, remember, 1 is that GH equals HG for any G. So again, we start, as always, let G be any. We want GH equals HG. So first, so the inequality of sets is usually proved, well, not usually, but quite often proved as 2 inclusions. Show that this is a subset of this, and this is a subset of that, and that gives you the inequality, just like we did there. So first, let's prove that GH is a subset of HG. So how do we prove that? To do that, take any element of H, okay, and we'll show that if I take this G that I've selected and this any H is in HG. Now we need to use 3 somewhere. Right? So if I do GHG inverse, okay, this is in this set, because that's the form of it. GHG inverse is in this set. This set equal to H. So this is some element of the subgroup H. Okay. Now if we have some element like this, if I multiply this equality by G, I get GH equals H G. And this is indeed in where I want it to be. Okay, so we've shown that no matter what G you take from G, no matter what H you take from H, the product of GH is in this set HG. So this is a subset of that. I won't bore you with the other subsets because it's just a symmetric proof. Just rewrite everything backwards and you get, all right, symmetrically. GH is a superset of HG. Therefore, they are actually equal. And that's the end of the whole proof. Okay. So I've said it before, but a subgroup H that satisfies the equivalent conditions of that theorem we call it a normal subgroup. Now, usually a normal subgroup, you don't use the letter H, but you use the letter N if you know it in advance. And our book doesn't use this notation, but it's quite common that this is denoted like this with a triangle. So H is less than or equal to with a like a triangle, like less than. Okay. Excellent. Now we go back to examples. Example 10.1 is that in an abelian, how do you write abelian with a little a or a big A?
Kelly even said something about this recently.
I don't know. I don't know. There's a guy who was called Abel, but then it became so
Use.
you know. So it's actually it means commutative. So it's become something that is not really related to that name, but it should probably be little a because abelian is something that has to do with Abel. But abelian, in this sense, only means it's commutative. Doesn't matter really. In the exam, you can use any.
It doesn't get marked down completely for not using capital A. Quite now.
Well, we're not in primary school. Even though sometimes I wish we were, well, no, but you know, some of the writing of some students. Well, it's probably big. I don't know. It might be dyslexic and whatever. So, in an abelian group, what are the normal subgroups of an abelian group? Well, you have the book, so there's no point asking the question. But any subgroup is normal. Why is that? Well, because, sorry, for any, if you take G and its subgroup H, and you take any element of G and any element of H, you get that GH is HG. And therefore, GH is HG. So that's boring. That's a boring example. We'll see. We'll see that it's useful. Well, we'll see some examples of the next phenomenon that I promised in the title, factor groups. What we'll be using that for some abelian groups. Example. And 2. So the group G is the symmetric group of 3 elements. Now this is really the first part. This is really example 6 too. So this is isomorphic to example 6 too, which we've seen before. And in this, you have first subgroup that's given here is that you take H to be, just shown it to you, 1.
The example
6.2 is 103, 104, something like that. But it really is just the same example.
Oh no, it's just so I can refer to it in the notes.
So here you get that 1, 2, 3. What am I doing? Yeah, 1, 2, 3, H is, well, the identity multiplied by 1, 2, 3 is 1, 2, 3. And 1, 2 multiplied by 1, 2, 3 is 1, 3. One way, but if you do it,
You explain how you get that many times when you multiply out.
I will do in a second. 1, 2, 3. It's the same. Here you get 2, 3. Say it again.
Right. So
this is just a notation for the identity. It doesn't. It's not really a. And this is 1 goes to 2, 2 goes to 1, 3 goes to 3. How do I get? So okay, 1, 2, 3 times the identity is 1, 2, 3. 1, 2, 3 times 1, 2 is, well, the convention we have is you go from the right as a compositional function. So if you compose the 2 permutations, 1 goes to 2, and 2 goes to 3, going from right, because you're writing, I should write it. So 1, 2, 1, 2, 3 is, well, 1 is mapped to 2,
yeah,
and then composing it is mapped to.
go backwards, don't you? So
Oh no, I wrote it in the wrong order. So this applies for the lower one. Sorry. Okay. 1 goes to 2, 2 goes to 1, so 1 goes to 1. Okay, and 2 goes to 3, and it stays there.
yeah.
And 3 goes to 2. 3 goes to 1, goes to 2. So this is an example for the lower one, for the top one. Well, it's not the same, but it's the same principle. Okay. So this is so this H is not normal in S3. That's an anti-example, if you like. A real example is when you take n to be 1, 1, 2, 3, 1, 3, 2. So these are all the even permutations. It's actually A3. And there are, so what's the index of this subgroup in S3? Yes. So it's the number of cosets. It's the definition, and there was a theorem which said that the number of cosets is equal to when you take the order of the group divided by the order of the subgroup. So the order of S3 is 6, 3 factorial. This subgroup has 3 elements, so necessarily there has to be 2. There are 2 cosets. And one of them is, in other words, this means, well, so here there are 3 cosets, and now there are 1 left and 1 right one. But there are 2 more and 2 more. That's the other sort. So of course, one of the cosets is always the subgroup itself. And the second is you can take 1, 2, n. You can take anything, because there are only 2 cosets. You can take anything that's not an element of n and take it as the g. And this is the same. It gives you the elements 1, 2. Well, it should give you all the 2 cycles on different positions. Okay. So these are all the odd permutations. The even permutations here, and the odd permutations there on the cosets. And it's normal. And in fact, what is true is that any subgroup of index 2 is normal. And this is exercise 10. Does it say in the exercise 10 is one of the submission exercises? So there you get the proof. When you have okay, we had examples. Now we should see some applications of well, applications. Something that they're useful for at the moment. The useful for is what's called factor groups. That's still 10-1. And factor group is so a factor group is sometimes called also a quotient group. Is when you take the cosets of a subgroup in a group and you define an operation on the cosets in the only possible way that you can, knowing what you know, and it turns out to be a group. So you could, we have these 2 cosets here, and you have an operation that this is the identity, so this times this is the identity, this times this is this, this times this is this, and this times this is the identity. That's the only way you can define it. Now the elements of your group are this set and this set. It's not just any thing, any odd element, it's a set, a coset. But scary, doesn't matter. You can usually, what we see is that you can in fact select representatives of the coset. So you could select the identity as the representative here, and you can select the 1, 2 as the representative there, and you just do a subgroup on these two elements. But you get something that's isomorphic. But in the factor group itself, this is a member. Okay. And the whole thing that we need to do is to prove that it actually is a subgroup. So a group, not a subgroup. Let n be a normal, but for that, we seem to need normality. Let n be a normal subgroup of G. And we define an operation on the coset of this normal subgroup in group G. So what is a coset? It's A times n. And we want to define an operation where we operate with another coset, B times n. And the only way that this can really be defined is we know how to multiply AB. That's an element of the group. N times by n. Okay. So the claim of this theorem is then the set of all cosets with this operation forms a group called G/n of order Gn. Zero. So I have cosets and I can now multiply cosets. Well, that's just a notation for that group, and the order is clear because that's as many cosets as we have by definition of index. And so if you want to prove this theorem, we can show that this is a group. The main hurdle really is that you want to show that this is well defined. And so if I take a coset, I'll take another coset, and I want to say this, the operation, the result should be this. Now, does it matter which A I pick? Because there are many different A's that give you the same coset, and many different B's that give you the coset. And what you want is to show that it doesn't matter which A and which B you pick. You still get, you always get the same set here, okay, the same coset. So, so order is easy because this is defined as the number of cosets. Okay. The number of group is on cosets, and so its order is the same as the number of cosets. But what is not so easy is the operation well defined. And to show that it's well defined, what we need to do is take a fresh sheet, not to run out. And got this. There's nothing that one could forget potentially. So we want that if I have two ways of defining one of the cosets, and I have two ways of defining the other coset, then if I do it this way, or if I do it this way, I get the same thing. If I don't, then the operation is not even an operation. It's just, we just don't know what to do. So that's what we want. So let's assume this. If we assume this, then A1 is in this set A1n because n contains the identity, and this is equal to A2n. So we have this, so there must be a witness in n which certifies that. So there is some, I'll call it m, well, I'll call it m. Don't get confused. There's a good reason for it, and you'll see in 25 seconds what the reason is, such that A1 is A2m. Yeah? A1 is in this set, so it has to be of the form A2 times some element of n. And in the same way as B1 is in B1n, which is B2n, so there is some, and now I call it n, so that I preserve the alphabet somehow. A takes n and B takes n. B1 equals B2. Now let's just finish this quickly. So remember, we still want to prove this. Okay, so then A1, B1, n. What is this equal to? Well, we know that A1 is A2m, and B1 is B2n. Rewritten, A1 is A2n, B1 is B2n. Now, because this is in n, it can get swallowed by this n. So it's going to be eaten like this. Because so if you have an element A2n, B2n, some element times some element of n, these two form an element of n. So so this is A2n, B2, because n is a group. And now this is A2m and B2. Oops. What can we do this? Don't give up yet. Yeah, so what can we do this? Exactly. It's normal, so B2n is n B2. Now you can see this. Again, this has been eaten because n is a subgroup or group. And this is now
A2, B2.
I won't take it back. It'll remain. Okay, so that's it. So this is what we wanted. Right? We wanted that. And you take two different descriptions of one coset, two different descriptions of another coset, then what you get as the result of the operation is the same coset. And if it wasn't, then we'd be doing good. Just and, this shows how it is. And we use the fact that n is normal. Without normal, we wouldn't get it. Well, not, at least not in this way. One of the coursework assignments is supposed to be for you to show that you really, if you want to do factor groups, you definitely need a normal subgroup. Can't do it without. But so far, I'm only telling you if you have a normal subgroup, you can do a factor group. So this is we've shown that it's the order is easy. What else does the theorem say? That it's a group. So is it a group? So far, we've only shown that the operation actually is an operation. Is it a group? Well, En, so that's n, is the identity. Check. And A inverse n is the inverse of an. Check. What else? It's associative. Check. Associative. So A, N, B, N, C, N is A, B, C. Doesn't matter how you. Doesn't matter which order you do it in. And I think that's it for and the order we did it. So that proves theorem 10.4. Because time is up. That's where we end today, and we'll start by looking at some examples of factor groups tomorrow.